In this video we derive the Dirac equation by knowing the Pauli matrices. Let's start from the relativistic energy equation, which can be written in this fashion. We have energy divided by the speed of light squared minus momentum squared p squared equal to mc all squared. M is the mass of the particle, the electron. Now we cannot simply replace operators into this equation because we would obtain an equation which is second order in time, the Klein-Gordon equation namely. And it doesn't describe particles with spin, so we still need to work on that. Therefore, what we want to do, and this was the Dirac idea, his idea was to rewrite this expression using operators, but by deriving an equation, first order equation. So an equation which does not contain the square of the time derivative. Now, to take into account spin, first we have to replace, for momentum, we have to replace the vector of Pauli matrices sigma, take the dot product with p. We can do this since p squared is equal to sigma dot p squared, and you can check the video before this one to prove this relation. But by doing so, we are also adding more components. We are considering spinors because this is a vector of matrices, and when you consider the square of this, yes, it is equal to p squared, but now it's as if we also have an identity matrix here, a 2 by 2 matrix, multiplying this thing on the right. Actually, this one here on the left, the identity matrix times p squared is equal to the square of this, which is a matrix, but it is equal to p squared, which is a constant. It is the magnitude of momentum squared, and then we have the identity matrix, a 2 by 2 matrix in this case. Now, by using these facts, we can rewrite this as E over C minus sigma dot P times E over C plus sigma dot P equal to mc squared. And now we are going to substitute operators. So for the energy operator, we know what to do. We have I h bar d over dx0. If we also put c into the time derivative, because the energy operator is I h bar d over dt. And if we put c and t together, we can rewrite this as I h bar d over dx0. Then for momentum, we have minus I gradient or del operator, so we can rewrite this as plus I h bar sigma dot del, the del operator, the gradient. And here we have I h bar d over dx0 minus I h bar sigma dot del. And here we have to put a function, psi, which is a spinor with two components, because we have introduced sigma. And then on the right we have mc squared times phi. Now we can reduce this equation to first order. Let's work on it. Now if we define phi L as phi and phi R as this part here, which is I h bar d over dx0 minus I h bar sigma dot gradient phi L, and then let me also multiply this by 1 over mc. It is just a constant. Well, these two together will imply that mc squared phi L, which is this part here, since phi is equal to phi L, that's equal to I h bar d over dx 0 plus I h bar sigma dot del, and here we have mc phi r, because as I said, this thing here is equal to phi r times mc, because we also have this constant here. Now, we want to rewrite only one equation with 4 components instead of 2 with 2 components. Let's rewrite these 2 equations that we found, these 2 here, in this fashion. So first, let's rewrite them like this. We have minus I h bar d over dx0 plus I h bar sigma dot del phi L plus mc phi r equal to 0, which is simply this one here, and I have rewrote it like this by putting these 2 operators on the left. So we have this expression here, and then we rewrite this one like this, minus I h bar d over dx0 minus I h bar sigma dot del phi r plus mc phi l equal to 0. Now let's take the sum of these 2 expressions and also the difference, and we obtain other 2 equations. In particular, these 2, we have I h bar sigma dot del, and then here we have phi l minus phi r minus I h bar d over dx0 phi l plus phi r plus mc phi r plus phi l equal to 0, and the other one is I h bar sigma dot del phi l plus phi r minus I h bar d over dx0 phi l plus, actually, minus phi r plus mc phi r minus phi l equal to 0. And now we define 2 functions, psi a equal to phi r plus phi l, and psi b equal to phi r minus phi l. And by doing so, we can rewrite these expressions, these 2 equations here, in matrix form like this: minus I h bar d over dx 0, then we have minus I h bar sigma dot gradient, and here we have psi a, and then we have psi b like this, because psi a is going to appear here, and it is equal to phi r plus phi l, and it's exactly this part. And then we have psi b that's going to appear there, and it is equal to phi r minus phi l. With this minus sign, we can also change the sign of these 2, and we are going to get this expression here. And then below we have I h bar sigma dot del I h bar d over dx0 plus mc psi a psi b equal to 0. So this is actually a 4 component 0, should be written like that, but never mind. And then what do we have? So we can rewrite this expression one more time. Let's factor out minus IH bar. Here we can rewrite 0, and this is actually a 2 by 2 zero matrix, so it should be interpreted like this. And then here we have sigma I, so I'm going to use index notation. This is the ith Pauli matrix. Then we have minus sigma I 0, a 2 by 2 zero matrix, d over dxi plus, and here we have I2, let me call it I2, so this is the identity matrix, a 2 by 2 identity matrix. Then here we have a 2 by 2 zero matrix, 0 minus I2, and this acts on the operator d over dx0, like this, psi a psi b plus mc psi a psi b equal to 0. And now we define this 4 by 4 matrix gamma I, whereas this matrix here is going to be defined as gamma 0. So using this notation, we can rewrite I h bar gamma mu del mu minus mc acting on psi, where psi is this 4 vector here. It's actually a vector with 4 components. So it's 2 spinors put together. We could say it like that. And this is equal to 0. And gamma mu del mu is also usually denoted as del slash. So this expression can be written as IH bar del slash minus MC psi equal to 0. And this is none other than Dirac's equation, Dirac equation. Let me remind also the expression for the sigma I, which are the Pauli matrices. Sigma 1 is the matrix 0, 1, 1, 0. Sigma 2 is the matrix 0 minus I 0. And sigma 3 is the matrix 1 minus 1, 0, 0. So we can also calculate gamma 1. So it's not a calculation, we just have to put together the two matrices sigma 1. So we have a 2 by 2 zero matrix here, and then here we have sigma 1, so 0, 1, 1, 0. Remember the expression, this expression here for the sigma i's. And then here we have 0, minus 1, minus 1, 0, 0, 0, 0, 0. Gamma 2 will be 0, 0, 0, 0, 0 minus I here. I 0, 0 I minus I 0, 0, 0, 0, 0. Gamma 3 is 0, 0, 0, 0. 1 minus 1, 0, 0. Minus 1, 0, 0, 1, 0, 0, 0, 0. And then we also have gamma 0, which is 1, 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, minus 1, minus 1, 0, 0. Written like that.